Now let's go through a few examples of how this theorem is applied. And so in each of these examples, we are going to figure out types of critical points. And so here is the system. So in order to apply the theorem, we need to calculate the Jacobian metrics first, which means we take, let me maybe elaborate on that. The first row of the Jacobian matrix is the derivatives of the first element of the right-hand side of the system of differential equations with respect to x1 and x2. So this is dx2 dx1 and dx2 over dx2. So this is 0, this is 1. And the second row, we take the second element here, and again differentiate it with respect to x1 and x2. So its derivative with respect to x1 is minus cosine x1, and its derivative with respect to x2 is 0. Okay, but the Jacobian matrix, of course, it depends on the variables at x1 and x2. So at each point, the matrix is going to be different. So now let's find the critical points. So in order to find the critical points, we need to equate both equations, the right-hand side, both entries of on the right-hand side to 0. So x2 is 0, and sine of x1 is 0, which means that x1 is a multiple of pi. I will write pi n, but since sine is 2 pi periodic, essentially there are two different cases. So either x1 is 0 or x1 is pi. So which means we have two critical points. So one of them is 0, 0, and the second is pi 0. So then there will be 2 pi 0, 3 pi 0, 2017 pi 0, and so on. But any other one is going to be either of these two types, depending on the parity of the coefficient at pi. So let us consider 0, 0 first. So at 0, 0, we substitute 0, 0 into the Jacobian matrix, and then cosine of 0 is 1. So the element at this place, at this position, is minus 1. So we have calculated the Jacobian matrix for the specific values of x1 and x2. And this gives us our linearized system. And the question is, what kind of a critical point does this linearized system have? And we can diagnose it using the techniques that we learned in the last lecture. The determinant is 1, the trace is 0, the discriminant is -4. So the linearized system has a center at the origin, which is a bit of a pity, because remember that the theorem that you just learned exactly is, so for a center point, the theorem doesn't work. So if the linearized system has a center at the origin, then the original nonlinear system has an unknown type of a critical point. Well, anyway, so let us go further, and let us do the other one, which is pi 0. And again, we substitute pi 0 into the matrix, into the Jacobian matrix, and then the matrix is different, 0, 1, 1, 0, and then its determinant is -1, which immediately means that the linearized system has a saddle point. And if the linearized system has a saddle point, then the original nonlinear system also has a saddle point. So hooray! This is pi 0, and we have theoretically proved that it has a saddle point, that this is a saddle point. Also, let me mention that this we proved theoretically, which is very good. So we just proved it rigorously, like mathematicians do. The other one, 0, 0, the theorem was inconclusive, but recall that in the last lecture we have calculated trajectories and we saw that trajectories are closed loops, closed cycles around this critical point, which means that it is indeed a center. But not because of the general theorem, but because of something else, because of our extra effort. But at least the other one, pi 0, we did it theoretically. All right. Now a new example. We also saw it in the previous lecture, and in the previous lecture we plotted the phase portrait, and recall that we kind of hypothesized that there is a spiral sink, and there is a saddle point, but we didn't prove it because we couldn't calculate the trajectories. But now we can. So now we can calculate the Jacobian metrics. Then again, there are two essentially different critical points, 0, 0, and pi 0. And at 0, 0, we can substitute this 0, 0 into the formula for the Jacobian metrics. And then here is the matrix of the linearized system. So this is just the Jacobian metrics for the specific values of x1, 0, and x2, 0. And then its determinant is positive, trace is negative, but the discriminant is negative. So the linearized system has a spiral sink at the origin. And now, according to the big theorem, if the linear system has a spiral sink at the origin, then the original nonlinear system has a spiral sink at the corresponding critical point, and it is asymptotically stable, which you can indeed see here. So this is the origin, and it is indeed a spiral sink. And the second critical point is pi 0. Again, we can do a linearized system. The determinant is negative, so it is a stable, it is a saddle point. So this one is a saddle point. Okay, excellent. Now the third example is going to be a little bit theoretical. Right, so suppose that we have a function of two variables, and then we can kind of transform it into the system of linear differential equations. dx dt is the partial derivative of the function with respect to x, and dy dt is the partial derivative of the function phi with respect to y. Then the Jacobian of the system of differential equations is, of course, going to be the Hessian matrix of the function. And I hope you still remember from calculus 3 how you can figure out the type of a critical point of a function of several variables, and how you can calculate the Morse index. So now I want to relate it to types of critical points in differential equations. Here is a little bit of a challenge for you to do it by yourselves. Let me just explain it on a specific example for a specific function xy. Right, so here, if we transform this function into a system of differential equations, then we are going to get dx dt is going to be the derivative with respect to x is x squared minus 1, and dy dt is going to be the derivative with respect to y, which is 2y. Now, there are two critical points. If the right-hand side is 0, then x squared minus 1 is 0, which means that x is plus minus 1, and y has to be 0. So we have two critical points, 1, 0, and minus 1, 0. So let me try to write somewhere further. So the Jacobian matrix of the system of differential equations, which is the same as the Hessian matrix of the original function, is going to be this. So the derivative of x dx dt with respect to x is 2x, then 0 here, and 2. That's the general form. Now, at the critical point 1, 0, we are going to get 2, 0, 0, 2. And at minus 1, 0, we are going to get minus 2, 0, 0, minus 2. Sorry, plus 2. Then one of them is a point of, in terms of the differential equation. This is a nodal source. And in terms of the function, this would be a local minimum. Right? And the other one is a saddle point in terms of the differential equation, and it is also a saddle point in terms of the function.